Hello everyone. Previously we learned how to calculate the rotational inertia of various continuous objects, just some specific ones like hoops and discs and thin rods. Right? And in every case though, what we calculated was around an axis through the center of mass. Well, what if that axis isn't through the center of mass? Right? How do we go about calculating the rotational inertia? Well, we could redo the calculus and change our limits of integration, right, for each axis. But that would require us to do that over and over and over again every time we changed where the axis was. Right? Is there a way that we can come up with something that will allow us to convert from an axis, from the rotational inertia about an axis through the center of mass to the rotational inertia about any axis parallel to that one? This is something called the parallel axis theorem. And so we are going to do a beautiful lab on this and a beautiful theoretical proof afterwards, right, to try to figure out how to do this a little more quickly. So the object that we're going to use is this one. Okay, it's a rod. It's got a bunch of holes in it. One of them is at the center of mass, and then the other ones are off the center of mass. So it can be screwed into the rotation motion sensor that we've been using in our other labs, right, at all these different places, changing the axis of rotation. Right, so we can compare one to the other. Problem is, while we could approximate this as a thin slab, or sorry, a thin rod, which has a rotational inertia of like, what, 1/12 ml squared, as we derived the other day, we can't, unfortunately, do that because it's got too much of a width to it this way. It's not just a length, but there's also a width. I don't care about the thickness, but I do care about the width of it. And it's enough to throw it off. Enough that it throws off given the quality of our data that we can get out of that rotary motion sensor. Okay, so kind of like in our other lab where we had to subtract off the rotational inertia of the rod so that we could focus on the point masses, we're going to have to treat this as something called a slab as opposed to a thin rod. So I am going to do for you now a proof which is not required by the AP and therefore will never be asked for you to do on a test, neither one of mine or the AP's. All right, to calculate the rotational inertia of a thin slab about its center of mass. But I'm going to do it anyway because we can. Now, there's quite a bit of calculus in this, so if we get to a point where the calculus gets a little bit too much for you, depending on how much calc you've had, that's fine. Right? Just kind of go on with it. You'll have, in the end, you'll have a math model you can use where you can plug numbers in and figure out the rotational inertia. It's actually on the sheet I'm going to eventually give you with all the other ones, typical ones. But on an actual AP test, they would give you the formula. Right? They would never ask you to derive it. So there's the center of mass, right? So this is an axis through the center of mass, through the center hole. And we're going to have to figure out here the rotational inertia of a slab about a perpendicular axis through its center of mass. Okay, that's what we're going to do the calc for. So here's our slab. The slab has dimensions A and B. A is the width, B is the length. We don't have to worry about the thickness for the same reason we didn't have to with hoops or discs. Right? Go back and look at those proofs if you want when we looked at cylindrical shells and solid cylinders. But we do need to know the width and length. Here is the center of mass. Of course, symmetry arguments would say, yeah, it's got to be right smack dab in the middle. So here are the things we need to know about this slab. We need to know the overall mass of the slab. In the lab, there'll be an electronic balance for you to place your slab. We need to know the width of the slab, A, and the length of the slab, B. Those, of course, you can measure with a ruler. So the rotational inertia of this slab about an axis through its center of mass is the integral of r squared dm. Remember that this is when we take the objects, break them up into little mass increments dm, and sum up all those little rotational inertias. Right? So here's our little mass increment. That little mass increment will have a mass dm. It is a distance r away from the axis of rotation, from the center of mass in this case. Okay? The density of the slab is constant. Hence, we can compare the density of the overall slab to the density of our little mass increment. But this is two-dimensional density. Has a length, right? Has a length and a width. So this is two-dimensional density, which doesn't have a special name or a special symbol. So like we did with the disk, we're going to compare the mass per unit area of the entire disk to dm over dA for our little mass increment. Okay? Now, what will the little dA piece be? Well, these are little rectangles or squares, if you will. So we have to go length times width. Well, that would be dx and dy would be our two dimensions of our little mass increment. You with me? So the mass increment has a mass of dm, and it has an area of dx and dy. All right, these are all infinitesimals. Right? The area of the entire disk is, of course, just length times width. It's a times b. Right? So that's where that came in here. Everybody see the substitutions I made? Solving for dm so we can do a change of variable. So dm is m over ab times dx dy. We plug that in there, we will change our variable. But then notice our variable will be in terms of x and y, not r. So we need to realize that we can break r, which is a two-dimensional distance, right, from the axis of rotation to the mass increment, into x and y parts. So there would be the x part. Notice that's parallel to the end, right, to the width. And there would be the y part. Right? That's how much of r is x and how much of r is y. And you notice how that makes a right triangle with r as the hypotenuse? So we can write r squared is x squared plus y squared. So we're actually doing a double change of variable here. We're changing dm into dx and dy, and we're changing r into, or r squared, sorry, into x squared plus y squared. Plug that in there. And so we get this. Now, this is the first time we've seen this where we have had two variables that we have to integrate. So we have to do what's called a double integration. And that's how you write it. Okay? We have to first take an integral with respect to x while keeping y constant. And then we have to take an integral with respect to y while keeping x constant. And I know this is weird, right? See if you can figure out here the little limits of integration. Sorry. Right? So for a, that would be, where's our mass increment this way? Right? The furthest to the left it can be would be negative a over 2. A is the entire width, right? So the center mass would be right in the middle. And the furthest to the right it could be would be a over 2. Our limits of integration for dy, which is this dimension, right, lengthwise, if it's all the way at the bottom, that would be negative b over 2. And if it were all the way at the top, that would be positive b over 2. So that's where I got these double limits of integration. Now, again, if this is just too wild a calculus for you, just let it kind of wash over you. See what you can pick up. Have some fun with it. Eventually, we'll come out with a math model. That's what you're actually going to use in the lab and going forward, okay? But if you can follow along with this, that's kind of cool. It's kind of cool seeing calculus applied in this fairly complex way. So, first thing I'm going to do is I'm going to factor out the constants, which are the total mass and the dimensions of the slab, right? M and AB. And then, like I said, the first step is I'm going to take an integral with respect to x, but I'm going to consider y to be a constant since we're integrating with respect to x. So, if we take the integral of a sum, that's the sum of the integrals. The integral of x squared with respect to x is fairly simple, right? That's 1/3 x cubed, or x cubed over 3. The integral of y squared with respect to x, well, if y is a constant, it's the integral of a constant with respect to x, which is just the constant times x. See that? X cubed over 3, x times y squared. All right, so that's taking the integral of each of these one at a time. And we have to evaluate that integral from our lower limit of negative a over 2 to our upper limit of a over 2. So we evaluate it at this minus that. So now I'm going to plug those in. Watch this. How about that? Now, I did a couple of things. Okay, I plugged this in here and here. I cubed it. I reduced it, right? And I wrote them here and here. So these first two terms are plugging in positive a over 2 for x cubed and for x. I did the same thing here and here for negative a over 2. We got to be careful. Remember that we subtract evaluating it at this. And since this is x cubed, that'll be negative. And since this is x, that'll be negative. So when we subtract both of these negatives, we actually end up adding two positives. That's why everything is positive in here, if you follow the negatives along. It's doable. Now we're going to combine like terms. A cubed over 24 and a cubed over 24 would be what? A cubed over 12. Ay squared over 2 and ay squared over 2 would be ay squared. Right, and there we go. There's like terms. Now it's a little more straightforward. Now we need to integrate with respect to y, and we treat x as constant, but there are no x's left because we evaluated it already. Right, so anything that's not a y is a constant. So again, the integral of a sum is the sum of the integrals. This a cubed over 12 is just a constant. So the integral of this with respect to y would just be this times y. The integral of this using the power rule, add 1 to the exponent, divide by the new exponent, which would be ay cubed over 3. Notice here a cubed over 12. Evaluated at b over 2, here and here, minus evaluating it at negative b over 2, here and here. Notice that when you evaluate at negative b over 2, this term would be negative, this term would be negative, and when you subtract those, they become positives. So we end up with something like this. Combine like terms. Here, first and third, I think. Or actually, no, all of these can be combined together, right? They're all like terms. Oh, no, they're not. A cubed times b and a cubed times b, the first and the third, and can be combined, and the second and the fourth, the ab cubes, can be combined. And here we go. Divide through by a, it will cancel out one of these, and it will cancel out the a there. Divide through by b, it'll cancel out the b there, and one of the b's here, and we are left with the rotational inertia of a slab about an axis through its center of mass, perpendicular axis through its center of mass, is m over 12 times a squared plus b squared. Now, if you notice, if we had treated this like a thin rod, the rotational inertia would have been 1/12 mb squared, right, where b is the length of the rod. So it's a little different than that because it still has the width in there. If we can consider the width, if the width is tiny compared to the length, then that's a good approximation to treat it like a thin rod. But if the width is sizable compared to the length, like in my picture, this width can't be ignored compared to the length, right? Then you need to use the more complex slab formula. Okay, so it's all about really how wide is it compared to how long it is. Like I said, with our device, it's close. Okay, you probably could get away with treating it like a thin rod, but it'll be more precise if you treat it like a slab. And certainly we can take a ruler and measure A, B, and a scale, an M, and we can calculate this out, right? Okay, so there's our thin rod, our slab, sorry, our thin slab. This is the axis through the center of mass. But we can screw this in at any other hole along the way. And if we do that, let's say we put it through this hole, right? Then our axis of rotation is here, and this would be a parallel axis to our original one through the center of mass. Now, how do we distinguish between this parallel axis and one through that hole or the hole on the outside? We denote where that axis is by using a quantity h, which is the distance from the axis of rotation, from the center of mass to the parallel axis. H is the distance from the center of mass to the parallel axis, which you, of course, can measure with a ruler, right? Especially if you go from hole to hole, right? I like how this device was made because you see how they put the little hole right at the edge and then the little metal piece around it, which pretty much means that this one is right at the end of the rod, right, while still making it able to screw in. Okay, so That's the parallel axis. So the purpose right here is to calculate graphical and mathematical representations of the relationship between the rotational inertia I of a body of mass m around a parallel axis of rotation not through the center of mass and a distance h from the center of mass to that parallel axis. So our three variables are rotational inertia, mass of our object, and h. Okay? Now, with this device screwed into the rotational motion sensor, I don't have a bunch of these rods of different mass. So we're going to keep mass constant. We're just going to use the one rod, right? But we can obviously vary h by screwing these in to different holes and changing the position of the axis of rotation. Don't worry, the mass will get teased out in the post lab. Okay, so we're only going to do a one stage lab here. We don't have to change mass and keep distance constant. All right, which kind of makes it nice. It's the way the equipment works. All right, now this equipment is going to work just like the other ones, right? Except we're going to have this thick slab right here, right, attached to it and screwed in. You're still going to use the big pulley, which has the same radius as it did before, right? And we need to be able to calculate the rotational inertia of that pulley. Well, that's going to be based on, just like in the other labs, the angular acceleration that it gets, which we can measure because we'll run the equipment just like we have in the last few labs, and we'll create a graph of angular velocity versus time as the mass falls and the string makes this spin. And then the slope of the angular velocity versus time graph will be your angular acceleration. With me there? So I'm going to go through the proof for the equation for the rotational inertia, experimental rotational inertia, right? Of these as you change where you're screwing in the rod, which means you change where the axis of rotation is. This is the same proof we've done before, so hopefully nothing new here. Going to go through it fairly quickly. So the torque here is, of course, provided by the string wrapped around the pulley. That's Rf sine theta, where R is the radius of the pulley, and F is the force of tension in the string. If you set it up as you have in the last few labs with your other pulley, tilted at an angle so that the string comes off tangent to the pulley, right? Then this force of tension acts tangent to the circle, and therefore the angle in between R, the radius of the pulley, or the distance from the axis of rotation to the point of application of the force, and the string, the force itself, is 90 degrees. And the sine of 90 is 1, so the torque is R, the radius of the pulley, times the force of tension in the string. Again, I hope none of that is new to you. What is the force of tension in the string? Well, we can figure that out by looking at the hanging masses. The forces acting on the hanging masses are, of course, gravity acting down and a force of tension acting up. Since these hanging masses are accelerating, because if they don't, then the rod's not going to accelerate, and they are accelerating down, the force of gravity must be bigger than the force of tension. Don't fall into the trap of saying these forces are equal. That would only be true if it was either not moving or moving at a constant velocity with no acceleration. Therefore, applying Newton's second law that the net force is the mass times the acceleration, the net force would be the force of tension up minus the force of gravity down, equaling negative ma, because the acceleration is also down. Up positive, down negative, no arrows left, now a scalar equation. Please use a conventional coordinate system unless you state that you're not, right? So we call down negative and up positive. Solving for the force of tension, plugging in that f of g is mg, factoring out an m, right? We now can calculate a force of tension if we know the acceleration of these hanging masses. Note the m is the mass of the hanging masses, and g, of course, is our old friend, gravitational field strength. But how are we going to measure the acceleration of these masses? Right? Well, we could do something lower tech. In the Newton's second law lab, the one way you could do that lab, or do it here even, is you could measure the time it takes these masses to fall to the table, maybe a stopwatch, right? And then along with the distance they fell, you could use the third kinematic equation to calculate a linear acceleration. That might be a lower tech way of doing the lab without the rotary motion sensor. We, however, have a rotary motion sensor, which we can use by taking the slope of the angular velocity time graph to figure out the angular acceleration of the device and of the slab, right, as it rotates. How do we do that? Well, we are going to realize here that since the string doesn't slip, right, on the pulley, the acceleration of the masses, and therefore the string, have to be the same as the acceleration, linear acceleration, of the outside of the pulley, which is a tangential acceleration because the string is tangent to the pulley. And we know how to calculate the tangential acceleration of the outside of the pulley. It is alpha r. This is an alpha, these are a's, right? Where r is the radius of the pulley. So, we measure the angular acceleration using the rotary motion sensor. We can calculate the tangential acceleration of the outside of the pulley, right, which is the linear acceleration of the hanging masses. We take that, we can calculate the force of tension in the string. We take that, we can find the torque. So this goes in here, this goes in here. If we plug them in so that we don't have to do so much calculation, we get this as an equation for the torque for this device. But of course, Newton's second law says torque is equal to I alpha, rotational inertia times the angular acceleration, which again we can measure with the device. So that means we can calculate an experimental rotational inertia by taking the torque and dividing it by the angular acceleration. But here's how we calculate the torque. Plug it all in, and we get the same equation we've used in the last few labs, right, for calculating the experimental rotational inertia, right, about whatever axis you screw into the of the slab that you screw into the rotary motion sensor, right, whatever distance h. Now remember, the r's are the radii of the radius, of the pulley, the big pulley, same as it was before. It's on your lab sheet. The m is the hanging mass, again on your lab sheet. Little g, the gravitational field strength, and alpha, these alphas, are the angular acceleration you will measure with the rotary motion sensor. Hopefully that proof is getting to be something you could do yourself if need be. Then you'd be ready for the next quiz, or at least closer to it. All right, let's take a look at the lab sheet here a little bit. So here's the purpose we had before, right? Here's our slab and center of mass right in the middle, parallel axis, a distance h away, slab of mass m. Part one is really just to measure the things we need for the slab and to calculate the theoretical rotational inertia about the center of mass. And eventually you're going to dump that into a Google form. Okay, so we can pull that out of the experimental part. All you need to know, of course, is this that we just derived. This is the mass of the slab. This is the width of the slab. This is the length of the slab. These had better be in meters and this in kilograms so that we get a rotational inertia in kilogram meters squared. Please make sure, even though you're using the ruler, you convert to meters, and you're using the electronic balance that you convert to kilograms. So you can just calculate this now. If that calculus was beyond you, that's okay, use this. Remember, this was not one required by the AP curriculum, and therefore you will never be asked to actually recreate that proof. You can do it, great. That means you probably can do any of the other ones, right? But it's, a little calc heavy. If they wanted you to do something like this, if they wanted to do a problem like this, they would give you this rotational inertia. Okay? I'm going to give you a sheet with a bunch of rotational inertias on there, including this one, right? So if you were doing a worksheet or something, you could just look on that sheet. But on an actual AP test, right, they would have to tell you what that is. So this is part one, really simple. You don't have to use any of the fancy equipment. Just unscrew your slab and measure everything, right, and then calculate it. So the second part of the lab is really the heavy experimental part. This is rotational inertia about the parallel axis versus the distance h it is from the center of mass to the parallel axis. Notice you're going to keep the mass constant here, right? You're going to use just the one slab. So these are the same kind of steps that you've used in the last few labs. Notice the radius of the pulley that we're putting into the equation is the same 2.4 centimeters, 0.024 meters. The mass, I want you to put a 20 gram, 0.020 kilogram mass onto the mass hanger. Should be the only one you have for this lab, right? Which makes a hanging mass of 0.025 kilograms, which again goes into the equation that you're going to use. Your first step is going to be to screw the rod in through the center of mass hole, the center hole, right? Which means H is 0, right? Because it's through the center of mass. So this distance in our lab sheet here, the distance H for your first one is 0 because you're putting it through the center of mass. You're going to measure the angular acceleration 3 times. You're going to come down here, calculate the average, and use it in our friendly neighborhood equation for the rotational inertia about the parallel axis with this M and this R. Right? These are the same M and R's I just told you about, right? Okay. Then you're going to go back and screw the rod in, right? This slab through every other hole on one side. You don't have to do, all the holes on this side if you do all the holes on this side, right? That's just symmetry. I think they did that just to make it symmetric mass-wise, to help it a little bit. You will notice that the data starts getting a little funky. The graphs start getting a little wavy when you get to the outside. And that's because I don't think they intended for the equipment to be used this way. And when you hang it, like say you're putting it through the last hole, it's going to have a little vertical torque on it, which messes a bit with the rotational motion sensor, but not enough that it throws off the data, enough for us. It still works pretty well. But if you get these kind of wavy graphs towards the end, you won't freak out, all right? It's just because of the way the equipment's set up. Once you finish that data table, this one, right, you're going to graph rotational inertia versus H, the distance from the center of mass to the parallel axis, right? So this versus, versus that, right? Rotational inertia versus that. So that's why I bolded those, right? Because those are the columns you're actually going to graph. Make sure you're graphing the right thing. It's not going to be a straight line, so you're going to have to linearize it, sketch your graphs. Here it tells you to go to the schedule sheet for this part and plug in lots of stuff. There's lots of stuff that we need to know to analyze this. You have to put in the mass of your slab, your theoretical rotational inertia of your slab about its center of mass, right? Those are both from part 1. And then here's the parts from part 2, the numerical portion of the slope of your linearized graph, and we need your y-intercept in this case. This is one of the few labs we do all year where the y-intercept is actually going to be meaningful for us and needed. So all 4 of those things will get plugged in there. If it doesn't take some of them, then you got to check and make sure. Of course, the most common one would be your slope, and that would be because of incorrect calculations. All right, so be careful with your calculations because using this equation can get a little tricky. But you've had some practice with it. And then there's some questions to answer, and then we will eventually do a post lab. This is going to take a while, right, to do this lab. So do it quickly, but don't hurry through it because we want good results and be very nice to the very expensive equipment.